Hello friends, subscribers and new viewers of this channel, and welcome to Control Theory and Signal Processing tutorials. In this tutorial, we explain the basics and C++ implementation of a finite impulse response filter. The finite impulse response filter is often abbreviated as the FIR filter. To make this video tutorial more interesting, here is an example of using finite impulse response filter. In this example, I'm using the FIR filter to reject noise, that is, to attenuate the noise. Over here you can see the noisy sinusoidal signal, and when I pass this noisy sinusoidal signal through my FIR filter, I get this response. That is, over here you can see the filtered output. On this graph you can see the comparison of the input and output of the FIR filter. The blue line represents the noisy input and the red line represents the filtered output. In this case, I'm actually using a moving average filter, which is a special case of the FIR filter. In this video tutorial, I will teach you the basics of FIR filters, and I will thoroughly explain how to implement the FIR filter from scratch in the C++ programming language. But before I start with explanations, here is the copyright notice. This video lesson developed code files and documents should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, this lesson and the provided material should not be used for commercial purposes and for training of engineers working in companies. This lesson and the provided material should not be used as lecture materials on online learning platforms and in university courses. This lesson and the provided material should not be used to train an AI algorithm or a large language model. First, we explain the basics of the finite impulse response filter, and later on we will explain how to implement the finite impulse response filter in C++ from scratch. The finite impulse response, or FIR filter, has the form given by this equation. In this equation, UK minus 1, UK minus 2, UK minus 3 until UK minus n are the inputs of the FIR filter at the discrete time instance k, k minus 1, k minus 2, k minus 3, and until k minus n. Yk is the output of the FIR filter at the discrete time instant k. Then B0, B1, B2, B3 until Bn are the FIR filter coefficients, and they are designed by the user. And finally, n is the order of the FIR filter. FIR filters have a large number of applications in control engineering and signal processing. The most simple and maybe the most widely used example is the moving average filter. Namely, for n is equal to 3, the moving average filter has this form over here. We can see that the output is the moving average of the inputs from the current time instant until the time instant k minus 3 in the past. Over here the coefficients are 1 over 4, 1 over 4, 1 over 4, and 1 over 4. Also, I have to mention that finite impulse response filters and finite impulse response models have a large number of applications in system identification and control theory. Namely, you can formulate a model of your plant or a model of the system that you want to control in the finite impulse response form. You can write this equation where UK minus 1, UK minus 2, UK minus 3 until UK minus n are the control inputs, B0, B1, B2, B3 until Bn are the model parameters, and Yk is the output of your system. You can easily estimate the model parameters from the input-output data by using a simple least squares approach. And after you have your model, you can use a model predictive control to design the control inputs. And this is a very effective approach. In the sequel, we explain how to implement the FIR filter in the C++ programming language. And for that purpose, it's a good idea to expand this filter equation for several values of k. Over here, we assume that n is equal to 3, that is, that the filter is of the order 3, and we start from the time instant k is equal to 3 inside of this equation. If we substitute k is equal to 3, and if we expand this equation, we will have that y3 is equal to b0 multiplying u3 plus b1 multiplying u2 plus b2 multiplying u1 and b3 multiplying u0. And by using the same principle, we obtain y4, y5, and y6. And you can continue with this approach. What is interesting over here to observe is that you can simply write b0, b1, b2, and b3, and then you can start u0, u1, u2, u3, then you can shift u1, u2, u3, u4, and you can continue with shifting the time index for the input, and finally you will get u3, u4, u5, u6. The finite impulse response also has a matrix form, and more about this in our future video tutorials. In the sequel, we present a C++ implementation of the finite impulse response filter. And over here you can see the main C++ code. This code uses several functions given in this file over here. And in this video tutorial, I will teach you how to write this code. But before I do that, let me give you a general idea. First of all, I will use Python to generate the input data. Namely, here is the Python script that I wrote. The purpose of this Python script is to generate a noisy input data and to save this input data inside of the text file. To show you how the data looks like, I will execute the code from here to here. And over here you can see the noisy input data. And this is precisely the example from the beginning of this video tutorial. This Python code will save this data inside of a file. To show you how the file looks like, here it is. It's a simple text file where the rows are the values of the input signal at different time instants. And this file has thousands of rows. Then, in the C++ code, we will use the functions given over here, that is this function, to load the data. And this function will create a vector on the basis of the data. That is, every entry of the input data vector will be a row from this file over here. Then, the main C++ file will define the filter parameters. Over here you can see the b values, and in this particular case this is a moving average filter. Then this code will fill in the vector, that is, it will create the input vector on the basis of the created function and the data, and then over here we implement the FIR filter, that is, we implement this equation over here. Once we do that, we simply create another vector storing the output data, then we save the data by using this function over here that's defined in functions file. This function will accept the vector data and it will simply create a new text file. And the new text file is given over here. It is actually called output data. That is, over here we store the filtered data. After we do that, we go back in Python and we visualize the data. Over here I will execute the second piece of the code, and the second piece of the code will show two things. It's going to show first of all the filter data on a single graph, and then it's going to show the input data and the filtered output data on a single graph. And this graph is very useful for comparisons. So let's start with coding. Okay, let's start with implementation and with coding. The first step is to create a Python file that will generate a noisy input data for an FIR filter that will be implemented in C++. This file will also save the noisy input data in a text file. So let's start. The first step is to import the necessary libraries. So let's import NumPy as np. And besides NumPy, we will also import matplotlib.pyplot as plot. So let's import matplotlib.pyplot as plt. Next, let's set the number of data samples. Here I will set the number of data samples to be 1000. Next, let's define the input file name. I will call the input file name simply as input_data.text. This is the file that will be used to save the generated noisy data. Next, I need to specify another file, and this file will contain the data that will be generated by the FIR filter. I will call this file as filtered file name. And over here, I will call this file as output_data.text. Good. Next, let's create an empty input array. To do that, we first need to declare the variable called input array, and I will set it to zeros. For that purpose, I will type numpy.zeros, and the shape should be s,1. That is, I will have only a single column and s rows. Next, let's generate a noisy input data. To do that, let's define a step size, for example 0.01 seconds, and let's create a for loop that will fill in the entries of the input array. So let's type for I in range, and over here let's specify the length of the input array, and then inside of the for loop let's simply type this: ith entry of the input array, and let's be careful over here, since we are dealing with a vector, we should write I, 0. This means ith row, 0th column or first column, and it should be equal to numpy.sign function. Over here, let's simply type I multiplying the step dt, and let's add random noise, 0.2 multiplying numpy.random.randn, and here it is. Next, let's plot the input array to make sure that the input array is properly generated. For that purpose, we need to type plot.figure, and let's specify the size of the figure. So for example, I usually like to create figures that are 10 by 8. The units are arbitrary. After that, let's plot. Plot. We need to specify what we are plotting. We are plotting the input array over here. Let's specify the color. The color will be blue. Let's specify the line width. Let's specify 2, and let's specify the label to be input. And that's it. Let me expand this such that you can see what I'm typing. Then let's add the legend. And after that, let's add the grid. Let's set the visible to be true. And after that, let's save the figure. We will save the figure as input .png file, and let's specify the resolutions in the dots per inch. I like to specify 600 dots per inch, and finally let's show our input. Okay, so that's the code. Let's select this and let's evaluate this, and let's hope that there will be no errors. Okay, no errors. Let's see our input array. Here is a plot. Here it is. Looks perfect. Now, let's verify that the file is actually saved as input.png. So over here I will go to my workspace folder, and here is my file. Perfect. However, we still didn't create a text file that stores all the data. Let's do that. Save the data. To save the data, we simply need to type this numpy.saveText, and over here we need to specify the file name. Here's the file name string, so I will simply type input file name, and over here I need to specify what I'm saving. I'm saving the input array. Okay, so let's select this and press F9, and let's verify that the file is being generated. Here it is. Here is the input data file. Looks good. The next step is to start with C++ coding. Next, I opened a command prompt and I navigated to my workspace folder. From my command prompt, I will start my favorite C++ editor, and the name of the editor is Visual Studio Code. To start the Visual Studio Code, I will type code with a dot. The idea is to create two C++ files. The first file will contain the definitions of functions, and the second file will be the driver file. So let's start with the creation of a file that will contain the definitions of functions. I will click on File, New File, and I will call the file as functions.cpp. And let's make sure that we save this file in the workspace folder, and let's start with coding. Before I start with coding, I need to mention the following. In this video tutorial, I will keep the implementation as simple as possible. That is, I'm not going to write a C++ class that will implement the finite impulse response filter. I will do that in the next video tutorial. The first step is to import the necessary libraries. First of all, I need to import vector. In this tutorial, I'm using vector to store the entries of the input and output vectors, or the input and output arrays, or better to say, the inputs and outputs of my finite impulse response filter. Next, I need to include input-output stream. I'm using this library since I will be printing messages in my command prompt. Next, I need to include fstream library. Fstream library contains declarations and definitions of functions that are used to open and save data to files. And finally, I'm using the string library. I'm using strings to define the file names that I will be using to store and load data from. And finally, I'm typing using namespace std. I like to type this since I don't like verbose typing. For example, if you don't include this statement over here, every time you're using an element of the STL or the standard template library, you'll have to type this std and then vector. And I really don't like this verbose type of typing. Instead of doing this, by including using namespace std, we can simply write vector. First, we will declare and define a function that will be used to load data from this file over here. That is from the input data file. So let's do that. Int load data. Load data is the name of the function. And let's specify the input parameters. This function will contain two input parameters. Here's the first one. it's a vector that stores doubles. Oops, let me type it. Good. And over here, the object is passed as a reference, and I will call it as loaded data. Okay, so what is loaded data? I will pass an empty vector to this function. The name of this vector is loaded data, and this function will fill in the entries of the loaded data on the basis of the entries in the file. That is, the function will read this file row by row, and it will fill in the entries of loaded data. Then the second input parameter is the string that defines the name of the file. I will call this string simply as file name. And over here, let's return 0 if there is success. Let me now briefly explain why I'm using integer over here. A standard practice in C++ programming language is to return 0 if the function didn't experience any error, otherwise we are returning any non-zero value. For example, we usually return 1 if error occurs. That's why I'm returning an integer value. Another thing to keep in mind is that over here we are passing parameters as references. This is done in order to optimize the speed and memory consumption. Okay, let's continue. The first step is to declare an object that is used to open a file and read data from the file. For that purpose, we are using the class ifStream. This class is actually defined in this header file, fstream. Then the name of the object is input stream. Good. Next, I need to declare a temporary variable of type double. This temporary variable will be used to store the current value of the data from my file. And we will use a for loop, or better to say a while loop, to read these values. Okay, next we need to open the file. Let me type a comment. Open the file. To open the file, we simply need to type input stream dot open, and we need to specify the file name. The file name is stored in this string whose name is file name. Next, we need to double check if we were able to open the file. For that purpose, we need to use an if statement, and inside of this if statement, we need to type this: if input stream dot fail, that is, if we were not able to open the file, then let's print a message: cout failed to open the input file, and let's end the line. Okay, and then let's return 1. 1 means there is an error. Okay, the next step is to read the values from our file. How to do that? Well, we will write a simple while loop, and over here we need to type this input stream, and then we need to use this overloaded extraction operator, and we need to type value. Let me explain what's written over here. Input stream, then this extraction operator value, will do the following. At the beginning, it will go at the beginning of the file, and it will read this value. This value will be stored inside of the value. If we were able to successfully read, this whole statement will return 1, and the while loop can be executed. Now, next time this statement is being called, we are going to read the second row. Then we are going to read the third row, fourth row, fifth row, and every time this whole statement will return 1. when we reach the end of the file, that is, when we come here, input stream extraction operator value will return 0 and while loop will stop. And in this way, we can read all the entries row by row from our file. What do we do inside of the while loop? Well, we just need to fill in the entries of our vector. So let's type loaded data, and to push the values we need to use the function pushback, and what we are pushing back, we're pushing back the read value. That is the value that we read from our file. So at the beginning, we're going to read this value. This value will be stored in value, and we will simply push that value to our vector load data. And that's it. Simple as that. Next, we need to close the file. To do that, we need to type input stream. Then we need to simply type close, and that's it. That's our function. Next, let's declare and define a function that will save data to a file. Namely, our finite impulse response filter is going to process the input data and it will produce output data. We need to save this output data to a file such that we can open that file from a Python script and such that we can generate plots. I will call the function as save data. So let's type it. Int save data. This function will have two input parameters. The first input parameter is a vector that will store double, and I will pass this vector as a reference and I will call it as data. This is the vector that contains output data produced by the finite impulse response filter. The next input parameter is the name of the file. I will call it simply as file name. And again, we pass these objects as references. Next, I need to declare an object that will be used to open a file and to save data to the file. For that purpose, I need to use the class ofstream. So let's type ofstream and let's call the object as outstream. The class ofstream, where of stands for the output file, this function is defined in this library, fstream. Okay, let's continue. Let's open the file, outstream.open, and the name is file name. Here it is. Next, let's double check that we were able to open the file. So let's type if outstream, and over here let's type fail. That is, if we were not able to open the file, let's print a message, cout could not open the file, and let's end the line. That's it. And let's return 1. And again, 1 means error. Next, over here, let's save the data to our file. For that purpose, let's write a for loop. Inside of this for loop, let's start with this counter that starts from 0. Then the condition is I smaller than data.size. The function size will return the total size of our vector, and then over here I need to increment I. Inside of this for loop, I simply need to store data I, so let's type data I, and I need to store data I inside of my file. To do that, I need to type outstream. This operator over here will redirect the output to the file. So what will happen is that we will store the value stored in data I inside of our file, and we will do it row by row. To make sure that we do it actually row by row, let's end the line over here. So again, what's happening over here? We open the file, and over here we store the value, and we end the line. And that's it. At the end of the day, you will see something like this, where all the entries are stored line by line. And that's it. Simple as that. Now, at the end, let's not forget to close the file, outstream.close, and over here, let's return 0. And that's it. That's our function for saving data. The next step is to create a new file that implements our driver code and the finite impulse response filter. Click on File, New File, and I will call this file as mainfile.cpp. And let's save it in the workspace folder, and let's start by including the necessary libraries. Again, we include the same libraries and we are using namespace.std. However, over here, we need to include, in quotation marks, functions.cpp. Make sure that there are no errors, that is, that we didn't make any spelling errors. Functions over here. Perfect. Here's our int main function, and let's return 0 over here. First of all, let's declare the input data vector. So let's type input data vector over here. Vector that will store double, and I will call this vector u. Namely, I'm following the convention and the notation explained at the beginning of this video tutorial. That is, convention explained over here. The input will be denoted by u, the output will be denoted by y. To be more precise, we will store all the input variables to the vector u, and all the output variables will be stored to the vector y. So here's our input. This is a vector that will store u0, u1, u2, u3, etc. Next, let's declare the output vector following the notation from the beginning of this tutorial. We will use y as the variable name. Next, filter coefficients. Again, following the convention and notation, we will use the letter b for the variable name. Okay, over here, we will also initialize the filter coefficients. Namely, I will implement a moving average filter of the order 9. I will have 10 coefficients over here. Why is that? Well, if I go back to the slide, if I look over here, this is a moving average filter of the order 3. And instead of 3 over here, we actually have 4. That's why over here, I will specify 10 entries. However, my filter is of the order 9. So let's type first entry, and let's copy everything. Now here's the second, here's the second one, third, fourth, fifth, sixth, seventh, 8, 9, 10. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Let's continue. Next, let's declare two strings, input and output data files. The two strings are called. The first string will store the file name that will be used to open the data, and this file name is input data.txt. Here's one very important remark. Namely, this name over here should match the name in the Python code. You can see over here the input file name, it's input data.txt. You can simply copy it here and you can paste it over here to make sure that they perfectly match. Next, we need to declare and initialize a string for saving the data. That is, we need to declare a string that defines the name of the file for storing the data. File name, let's put here output. And again, let's go to our Python file, and the file name should be output data.txt. And let's paste it over here. Perfect. Next, we need to declare a variable that will store the filter order. So I'll type assigned integer n, and then I will take my vector b over here, then I will get its size. The size is actually 10, however the filter order is size -1. And that's it. Next, I need to declare this variable that will store the current value of the output. Output value, I will simply call it like that. That is, this variable will store y of k, this value over here. And it will be computed in a for loop that I will define later on. Okay, so let's continue. Next, we need to load the data. To load the data, we need to call this function. So let's copy this prototype of the function over here and let's paste it over here. This function will return a variable called status. Then we need to specify the array name that we want to fill in. The array name is simply u, and we need to specify the file name. The file name input string stores the file name, and that's it. Now let's check the status. If status is equal to 1, means we were not able to read the data. Let's simply return an error. So we can type exit 1. This will stop the code and it will return the error code 1, which means we were not able to open this file. Next, let's continue. Our next step is to implement the FIR filter. So let's start. First of all, we will define a for loop that will loop over the values of k. The value of k is actually a discrete time step, and we will need to iterate until the end of input vector. So let's do that. Over here, let's type for, and let's define an iterator. Assigned int, I will call it k. Oops, not L, it should be k. Then k is smaller than u.size. Okay, u, after this command or after this statement, will contain all the entries from this file. That is, it will contain 1000 entries. And by typing u.size, we are actually returning the total number of entries, and in our case, that's 1000. And then over here, we are simply incrementing the discrete time step. And here's our outer for loop. Now, over here, we need to be very careful. Let's go back to the filter equation. Here it is. Here is the example. As I explained previously, this example is written for n is equal to 3 and k is equal to 3. Note from the general equation that in this particular case, we cannot compute u0, u1, or actually I have to be more precise, we cannot compute y0, y1, and y2. Why is that? Well, if you look at this iteration over here, and if you see over here, the iteration needs to start from y3. If it starts from y2, y1, or y0, we will not be able to get the input values. Namely, the subscripts of input values will be negative and they're not defined. Consequently, I will fill in the values of the output y initially with zeros until we reach to this step over here. So over here, I need to type if k is smaller than or equal to n minus 1, then what do? We simply say this. Output value, that is the value of yk, is simply 0. In this way, we deal with the boundary effects. Otherwise, that is after k is greater than n minus 1, that is, after this time step, we can clearly and accurately compute outputs of y without worrying about boundary conditions. So let's do it over here. Let's start with the second case. Over here, I will initialize the output value to be 0 again. And then what I will do, I will define a for loop that will simply compute the right-hand side. To do that, we need to type over here for unsigned int j is equal to 0, j is smaller than or equal to n, then j plus plus. Then we will simply, in this for loop, type this. Output value is equal to the previous output value plus the coefficients. The coefficient by multiplying input k minus j. And that's it. Simple as that. What are we doing over here? Well, we are simply computing the right-hand side, and we do it iteratively. Namely, this for loop will iterate through the values over here, and it will add them. At the end, after for loop is executed, output value will store the value of y3, y4, y5, or y6, depending on the current value of k. After we do that, over here outside of both if and else conditions, we need to simply type this. Y dot push back, and we need to push back the output value. And that's it. And finally, we need to save the data. To save the data, we need to type status is equal to, and note over here that status is already declared, so I don't need to redeclare it. So I simply have to call the function save data. I need to specify what I'm saving y, and I need to specify the file name. So I'll simply copy this variable over here, paste it over here, and that's it. Then again, if status is equal to 1, then we simply return 1, and that's it. Simple as that. This is our driver code. Okay, so let's save this file and let's compile the file. To compile the file, let's go back to the command prompt. Let's see all the files over here. Here's the main file and here's the functions. Let's go back to the main file and make sure that include functions.cpp is added. Then let's go back over here, and to compile the file, I will be using the GCC compiler. However, you can use any other compiler. You can also compile the file directly from Visual Studio Code. To install the GCC compiler, I use the mingw installation package. Okay, so let's type G++, then I will use the option W all and W. These two options will actually display all the warnings and all compilation errors. Then after that, I need to specify the output file, that is the executable file. I will call it as FIR, and I need to specify the source file. The source file is mainfile.cpp. And let's hope that we don't see any warnings or errors. So let's press enter. Perfect. No warnings, no errors. Let's now press this command. Let's locate the executable file. However, before executing this file, let's close all the text files that we previously opened, since we don't want to create some opening errors in our code. And so let's type FIR and let's press enter. Bang, here it is. Okay, so let's verify that this code was actually properly executed. Let's go to the C, let's go to our FIR, and over here you will see the output data. This file is being generated by our code. Let's open the file, and here it is. And let's analyze it. Okay, we can see 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Perfect. These zeros come from the boundary effects, and they are actually created by this piece of code. Then after we have enough inputs to compute the output, we are filtering the data over here until the end, and looks perfect. Okay, now let's go back to Python and let's now write a piece of code that will plot the data. The code will be similar to the code that we previously wrote. So first of all, let's load the output data. So I will define an output array over here, and then I will use numpy.loadText, and I will specify the file name. The file name is filtered file name, and that's precisely this file name over here. Good. Next, let's plot the output array. For that purpose, I'm going to simply copy this code, paste it here, and I will modify it. I will use red line over here. The output should be filtered output. Then what I need to specify, I'm going to save it as output.png, and let's use the same dot per inch. And over here, let's specify that we are actually plotting the output array. Okay, so let's verify the code, defining the figure size, plotting over here, red line. Let's specify the line width to be 4, adding legend, grid, saving the figure, and showing the plot. Perfect. Let's now erase everything what's being written previously, and let's now execute this. To execute this code, I first need to generate a new random input and to save it to a text file. So I will do it like this. Here it is. Then I will execute my C code again. Here it is. Then I will go back to Python and I will plot the output array. First of all, I will load the data and plot it. And here it is. Looks beautiful. However, we need to plot both the input and output data on the same graph. So let's do that. So what I will do over here to save time, I will simply paste this piece over here, plot the output and input arrays. Then the figure size will be the same. Then I will simply take this piece from the input. I will paste it over here. First I will be plotting input. Let me increase the size here to 4. Then I will be plotting the output. The colors will be different. And I will call the file as output input.png. So let's verify that everything is okay. It is. And let's plot it. Simply select F9 and here it is. Looks amazing. And you can see the effect of our finite impulse response filter. You can see how we are able to nicely filter the data. Okay, that's all for today and thanks for watching.